All right, so welcome back, everyone. Today we'll continue on what we left off last week after we talked about DRAM. And we kind of left off with like, okay, here are some of the requests that go to DRAM, right? And then what would happen to them when you schedule them together and it share the DRAM resources. We kind of left with this, right? Reliability. And we kind of talk about things that can go wrong about DRAM, right? For example, there can be errors in DRAM cell, capacitor loss, charges over time, right? And you can have faults, right? And we did talk quite a bit about this problem of DRAM lose charge over time. Basically, when you have DRAM, you have charge leakage where the capacitor will gradually, right, lose its charges, right? And it leaks over time, so you basically have to do a DRAM refresh, which basically means that once in a while, the controller, right, would need to write the same data over back to the same cell, right? And we talk about multiple techniques to kind of take care of that. In modern day, you have things like smart refresh on your CPU that would kind of periodically burst refresh on a few rows of data, and then it allows the CPU to basically resume and continue on the execution quickly, right? Then we kind of left off with this, right? Memory cells actually can be impacted by external environment because these are physical things, right? So if you heat the DRAM cell up, it's gonna be affected, right? It's gonna be less effective at storing charges. As it gets older, right, the cell would be not as effective at storing charges as well. Some cell will be impact by the number of writes that happen to the cell, or even things like random particles in the air that hit the cell in the right way. It can actually bounce off the electrons, right? And this factor basically cause bit flips. So let's look at this particular plot, right, from HPC 2017 to show how technology nodes, as we scale, as we make the transistor smaller, right? And you might have noticed even with this, right? The plot looks at something like 10 something nanometer, right? Which is actually bigger than what we have right now, bigger than what we have right now. But the trend is actually bad. Think about it. This is a log scale, right? This is log scale. It's 10 to the 3, right? So this thing is in the log scale. So it's 10 to the 3, 10 to the 4, 10 to the 5. Every time you go one step here, it's actually 10 times worse. Why is there a bug in the plot? It's 10 to the 5 twice. Actually not sure about that. But if you're looking at this technology, you know, it's about right where you look at, like, as you go up the scale, right? You're at about 10 to the 4-bit error rate. This is the rate where you will see bit flip, right? So as you decrease the cell size, you increase the capacity of your DRAM, but you also increase the error rate. Because your material that you use to build DRAM get thinner and thinner and thinner and thinner. You also have the increased variance in the cell retention time where it's stored. Retention time is the time the cell can actually like retain the electron in the cell, right? So when you increase when you scale down the technology node, make transistors smaller and smaller, the variance between the good cell and the bad cell get wider and wider. So your DRAM can run into more error, right? DRAM can be inaccurate, which sometimes results in, for example, the blue screen that you see in Windows where it just crash everything and you get some error code. Some of those actually happen from bit flips, right? And we have that, right? The problem is two things. First, can we detect it? And can we correct it, right? So detection and correction are the two important things. Anyone here heard about this DRAM called ECC DRAM? This thing. Anyone here heard about this term before, ECC DRAM? It does stand for error correcting code. All right, I see someone typing, so. Oh, okay, that's fine. So ECC DRAM is actually a common type of DRAM that go into your server, for example, right? Because one thing about server is you want to make sure it stays on. It's not like getting reboot because of some random bit flip, right? So if you want to build a server, one safe thing you can do is buy ECC DRAM. These are DRAM that can correct itself when it detects bit flips. Modern day ECC DRAM can probably tolerate around like 3 or 4 bit flips per a unit of data size. For example, one row of data, right? So when you buy this ECC DRAM, your server would be more reliable and it won't get rebooted because of random bit flips. And which means that it can help mitigate the problem, right? And if you think about it, right, if you look at encryption and like coding in general, right, there are multiple ways you can detect and correct error. One idea is, can we add more bits to detect error? You can use something like a Hamming code for this. You can use ECC DRAM. You can use newer technology, IECC. And now let's talk a little bit about the Hamming code and set that single error correction, double error detection. This is one of the basic scheme that I guess if you go into like computer engineering degree and do undergrad, SecDet is something that should be covered, right? Basically, the idea is I will add additional bit to detect the bit flips, and the purpose of those additional bits is to XOR the data bits to make sure that you now encrypt with the ability to detect error, because if you have a bit flip, if you have single bit flip, the XOR would change, but the XOR bit would tell you, hey, something is going on, because when you XOR every bit, let's say it's supposed to be a value 1, right? You XOR everything, and let's say the correct result is 1. When you have one bit flip, you XOR everything again, the result would change because of that one bit flip. So the XOR, the result will be 0. So in that way, each additional bit, which we call the parity bits, is put in there, right, to protect your data. And you use multiple parity bits to detect the location of the error. SecDet would use log n plus 1 parity bit, right? Because we don't have a lot of time, actually right now we will not do an example of SecDet, but here is an example on the slides, right, that you can try to practice. Oops, sorry. Over here is the parity bits, right, and this is your data. And you can use the pattern. Basically, the parity bit at this position will XOR everything. When you have the letter X, it means I XOR that bit. The parity bit at number 9 here would XOR just bit number 6, bit number 4, bit number 2, and bit number 1. Parity bit at bit number 10 would XOR bit 5410. And parity bit at position 11 would XOR the first 4 bits. In that way, right? In that way, each of these parity bit would tell you 2 information, whether there's a bit flip and where. If there's one single bit flip, it can tell what bit has the bit flip. All right. If you're curious, feel free to check back with me so I can go through this example after the class. The other thing that we would like to talk about, because it's more the graduate level concept, is, hey, if you buy DRAM, right, can you push the DRAM toward the limit? Anyone here try to overclock your computer before? Anyone? It was something that's more common again. I think back in the day, but these days you don't like always go to the BIOS and overclock things, right? But one thing you can do is you can push your DRAM, for example, toward the limit. For example, right? Right now you have the DRAM timing. How much do you have to wait to pre-charge? How much do you have to wait to activate just the row from the DRAM cell to the row buffer? And how much time do you have to wait until you finish reading? But because DRAM cells are not created equal, right? If you buy a good DRAM, a really, really good and reliable DRAM, for example, you might be able to overclock this a little bit and make your clock faster. You spend a little bit less time to activate and pre-charge, and in most cases, you might be fine, right? So can we make DRAM faster? Idea one, yes, we can overclock DRAM. Idea number two, which might be a little bit safer, is can we selectively overclock and oversupply DRAM, overcharge portion of DRAM to make them faster? You can also think about, hey, can we make DRAM to consume less power? That is also possible, right? We all use laptop. Right? Everyone here owns a laptop, right? If you look at the DRAM specification, it would say LP. Oops, sorry. Why can't I? Microsoft. If you look at the spec, it would have the letter LP, similar to the ECC DRAM. ECC is error correcting code. LP stands for low power. These are DRAM that designed for your mobile phone, your laptop. It used less power. It used less of the supply voltage. It used less of the supply voltage. So it dropped the voltage level, which means that it P equals IV, right? Power equals current multiplied by voltage. When you drop the voltage, you can then save power. So that's another thing you can do. What else can we do? Other memory technology, right? The question is, hey, do we always need DRAM? That's actually advanced in memory technology where you have things like 2D tile DRAM. So instead of having the DRAM plugging into your motherboard, these are soldered on DRAM tiles that are next to each other to increase the bandwidth. Your GPU, if you buy a fancy GPU available in the market these days, like for example the A100, you will be having the 3D stack DRAM. It's actually called HBM or high bandwidth memory. It's actually put DRAM chip on top of each other, connected through this unit called through silicon via TSV. Which connect each layer. So you get a lot more internal bandwidth. You actually also get a lot more external bandwidth to the CPU. You can also use a totally different material called the non-volatile memory. So the property of the non-volatile memory is the way it works, right? It's going to be different from DRAM. When you put data in there, it stays there. That's why it's called non-volatile, right? And you can think of it as this is in the similar, like the volatility is similar to SSD, where you put the data in the SSD, it stays there. So that's a non-volatile storage, right? There are multiple types also of non-volatile memory, which is you can have the, for example, the phase change memory or the RRAM or memristor, like spin torque MRAM, for example. There's more then that actually there's more types that are in, I guess, in the research phase right now, right? There are multiple that people are looking at, and people are trying to architect them to make sure whether they work. They also, similar to SSD, they comes with the downside of like, if you want to write to the cell many times, it would die, right? So you have to think about how do you handle writes for the PCM and STM RAM, right? You can also look at, if you look at 3D stack DRAM, right? It allows DRAM to be on top of each other or tile them close to the CPU, which also allow the base. Basically, the way 3D stack DRAM works is you have the base layer on top of the DRAM chip, which means that I can put some simple logic gates like adding or bind a simple like a logical operation in there. It means that first of all, you have a lot more bandwidth. The second benefit is you have something like a mini ALU in there in the logic layer, which means that this green thing, or this green thing, can be, for example, programmable. Or you can put some compute in there, right? It means that it's capable of processing some data right before it passes the data to the CPU. So these are some of the things that people actively look at and see what can be done, right? What can be done to make your application faster. There's an area called processing in memory, which means that we look at this layer and think about, okay, what are useful things we can do to make application more efficient, things like power efficiency or getting more performance. When you have multi-layer of DRAM chips, right? Also increase the capacity. Like the AMD GPU that has tiling, and these days the modern day GPU with the server grade, you have the high bandwidth memory as well, right? And again, as I said, it's connected to the true silicon via. It offers a lot of internal bandwidth, also a lot of external bandwidth. So that's the benefit of 3D stacking, right? It can be put on the same die as a processor if you will. So the bottom layer can process the data, and it allows for processing in memory, which means that, for example, now that you can have basic ALU elements in there, right? You can have you can basically limit about the data transfer. For example, we did a study about 4 years back that looked into Google workload like Chrome, video rendering, for example, and look at how much data are being moved around between the CPU and the memory. And we conclude that if we can perform processing in memory to pre-process some of this workload, right? You can actually save a lot of the bandwidth and improve energy efficiency and sometimes performance. You can also, that also comes with some complication. For example, when you run some of the code on this logic layer in the processing in memory, right? You might run into the case where the CPU modify the data in the memory, and then this logic layer needs to see the updated version of the data. So you need to figure out what get executed on the PIM core and how do you actually enabling consistency, which we will talk about in a bit, right? You also have things like non-volatile memory where the cells are no longer capacitor, which means that I don't have to refresh, which is a good thing. It means the charge doesn't leak over time. It's also denser than DRAM. So now you are looking at like terabytes and terabytes of memory. And again, you don't need to refresh the data or the time that you have to actually refresh the data a lot less often. But the problem is, well, this is a good thing. It's actually faster and much faster than SSD, but write to NVMe are destructive, right? Similar to SSD. So basically, when you look at non-volatile memory, the benefit is larger. You have a larger memory, right? Data is persistent. You don't have to refresh. People also think about, okay, what if we use this non-volatile memory to recover from a crash? For example, you have to reboot and you put the data in from the kernel in the non-volatile memory can be recovered from the crash, right? There's no leakage power, so it's much more power efficient. And it can be used in combination with DRAM. For example, the Intel's Night Landing, right? Which offer hybrid memory, right? You can combine DRAM and non-volatile memory together, hopefully to get the best of both worlds. You can use the DRAM, for example, as a cache to the non-volatile memory. So it's a paper proposed by Nguyen Qureshi back in 2009 that talk about the memory system that focus on the phase change memory. You can also look at so one of the work we did, I think this is back in 2012, if I remember the year correctly. We check whether the time, what's the time it takes to process raw hit, and it turns out row hit to DRAM and row hit to NVM is the same because it's the exact same sense amplifier. So if you read on the row buffer, it takes the same time. But if you have a row miss, NVM takes longer because it's a different material, right? So one of our idea called row buffer locally aware DRAM is to place the data in DRAM if you have a high row buffer miss rate. If you're not likely to get a row hit, put that in DRAM. If you're likely to get a row hit, I mean, it doesn't matter. Just put that in NVM because you don't see the penalty of putting data in NVM. So the idea is this, as I said, right? We classify application into two classes. The application with frequent number of row miss, and the application that has a really good locality, and you have a lot of row hits to the row buffer. So in the general cases, you basically can group them together, right? But if you frequently hit in the row buffer, it's better to put this row C and row D to PCM or non-volatile memory because it will hit in the row buffer and we will not see the downside of PCM or NVM, which is it takes longer to access data. And then application that miss frequently in the row buffer can stay in DRAM. And here's some example. Let's say you have access pattern to the main memory to row A, B, C, 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 A, B, D, 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 and then A, B, right? So these are row number A, B, C, and D. Default, right? A default solution that unluckily puts C and D's, which has a high row buffer hit rate to DRAM. It would service both of these two rows C and D, grouping them together, and you have 4 row hits, right? 4 row hits. And then all the row miss requests go to PCM. And the stall time to process this row miss request would be longer. So your application actually stall for a long time, as you can see on the top plot here. But with our solution, right, you basically put row A and B to DRAM. It might have a lot of row misses. We don't care because it does take, in total, less time to process all those row hits, while at the same time, even though the row miss request will take some time, but then you have more row hits. So at the end of the day, the overall time it takes is faster. So you save some cycle, right? So the DRAM and PCM system that is aware of this row buffer hit rate would basically stall less, right? And the idea of our dynamic mechanism is basically, hey, can we adjust to the program change periodically just to figure out what the threshold to put things into NVM? So we published this work at ICCD and we did the best paper, got the best paper award out of this. It's called Row Buffer Locally Aware Caching Policy for Hybrid Memory. So that's one thing you can do with non-volatile memory, right? Quick thing now that I talk about a bunch of papers that come up, right? So basically everything I talk about here, except for the basic concept of DRAM refresh, will not be on the exam. So these are more of the, hey, let's discuss the ideas that's been proposed in the last 10 or 15 years and see where things are going, right? So it's more of the discussion, less of the actually like, okay, these are the theoretical side of things you have to remember, so you don't. I want you to see the picture of where the future leads, as especially as for you guys who do not basically primarily focus on the architecture side of things, right? You might be seeing this device coming out in a 5 to 10 years, for example. Resistive RAM or memristor is another popular type of NVM, right? And the interesting property of RAM is the cell naturally perform a dot product in order to read something from the cell. And the bit line, instead of carrying the electron and just look at the 1 and 0 data, because the cell performs the dot product, the bit line actually becomes the sum of products. The thing is, sum of products is actually a part of matrix multiply. What does matrix multiply useful for? Many things, including a collection of machine learning application like CNN, right? So there's been ideas that's proposed in multiple papers throughout, I think, starting from around 2015. For example, Isaac is one of them that used ARM cell structure as a way to accelerate CNN and DNA, because these are the cell structure of ARM. You first need to convert digital signal to analog. But once it's analog, ARM cell essentially becomes a resistor, and with Ohm's law, right? V equals IR. So the resistor, when you want to read the value in your resistor, you basically the voltage, right? The current that go through, becomes the dot product, right, of the voltage and the resistance. So you can actually use this observation to perform a vector matrix multiplier. So on one line here, right? One line right here. I need a pen. Why can't I use a pen? So one single line here, right? Perform multiply accumulate. So when you have the whole cell array, this is a vector matrix multiplier. Right. So this paper is proposed 6 years ago in ISCA 2016. There has been a bunch of follow-up work to kind of figuring out what's the best way to actually perform things like matrix multiply. I have some work right now that also look into graph application and how to actually accelerate graph application using ARM as well. All right. So that's it about the topic of DRAM. So let me pause here for a little bit so we can take a break. All right.